It's your boy, Categorical Inference, here with some chi-squares. We're going to talk about the chi-square distribution itself, chi-square goodness of fitness test, the chi-square test for independence, and the chi-square test for homogeneity. So the chi-square distribution itself, it's a different distribution for the number of degrees of freedom. Very similar to the t distribution, how it's got a bunch of different distributions depending on the number of degrees of freedom. So the more degrees of freedom, the further the peak of the chi-square distribution is to the right. So it's the chi-square distribution with 1 degree of freedom starts like that, and then 2 degrees of freedom is like that, and then at 3 degrees of freedom we finally get this little hump. 4 degrees of freedom looks like that, etc., etc. So we get this peak, and that peak is slowly moving to the right. I think I might be showing you left because mirrors and everything, but it's slowly moving to the right. This implies that as you increase the degrees of freedom, you're also increasing the mean, the median, and the mode of the chi-square distribution itself. I do want to point out, no matter how many degrees of freedom, though, the chi-square distribution is positive. There's no such thing as a chi-square that's below 0. The chi-square goodness of fit test. This test, if a distribution of proportions is correct for a single population. I don't really like how I wrote that. Let's say the null hypothesis is the hypothesized distribution of something is correct. That'd be your null hypothesis. So it tests if a distribution of proportions is correct for a population. So this is one population, one variable. The conditions, you got to have randomness, you got to have 10%, and all your expected counts have to be at least 5. Yes, you have to write all the expected counts down. The way that you're going to run this is you're going to go into lists. You're going to enter your observed and your expected, and then you do the chi-square Goff test. And then it'll spit out your chi-square, your degrees of freedom, and your p-value. Those are the three things you have to report. So you're reporting the chi-square, the p-value, and the degrees of freedom. Degrees of freedom, though, incidentally, is just categories minus 1. And I think I'm out of things to say for that now. The chi-square independence test, it tests to see if two variables are related in a single population. So it's testing for an association of two variables. The null is that the variables are independent. So variable A is not associated. Apparently I'm very bad at typing, but variable A is not associated with variable B. Same conditions as before. The expected counts, the way you get those, row total times column total over table total. Also, when you just run the chi-square test in your calculator, it spits out all the expected counts for you. Remember, this is the one where you're going to go enter matrices. You only have to enter your observed ones because the calculator is going to give you the expected ones. And then you're going to run the chi-square test. The chi-square test for homogeneity is mathematically identical to the chi-square test for independence. The difference is primarily in the sampling. So it tests to see if a variable is distributed in the same way in multiple populations. So the test for independence, you're sampling from one population. The test for homogeneity, you're sampling from multiple populations, or you're doing an experiment. Experiments are always tests for homogeneity. The null then is that there is no difference in the distribution of the variable in the two populations, or 3 populations, or however many you need. Mathematically, again, though, matrices, enter your observed, and then run a chi-square. Conditions are the same. For both the chi-square test for homogeneity and independence, your degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Problems. In order to plan its next advertising campaign, the trendy motor vehicle company is investigating whether the type of vehicle and the color of vehicle are related. Each person in a random sample of size 275 selected from the company's mailing list was classified according to the type, car or truck, and the color of vehicle he or she drove. The data are shown in the table below. Which of the following procedures would be the most appropriate to use for investigating whether there is a relationship between vehicle type and color? Okay, clearly it's not a two-sample t-test, a two-sample z-test, or a matched pairs t-test. One, because those are all quantitative tests, and we're doing categorical. Two, we are in the chi-square video. But those are all quantitative, and this is categorical. So now, is it goodness of fit or independence? Well, luckily, they actually made it easy. They didn't make you pick between homogeneity and independence. They just made you pick between goodness of fit and independence. Those are very different. If this was goodness of fit, it would look more like that, right? There would only be one population, one variable. But since we have one population and two variables, it has to be the test for independence, not goodness of fit. That's what I thought. I just wanted to check. Product advertisers studied the effect of television ads on children's choices for two new snacks. The advertisers used two 30-second ads in an experiment, 30-second television ads in an experiment. One ad was for a new sugary snack called Choco Zooties, and the other ad was for a new healthy snack called Apple Zooties. For the experiment, 75 children were randomly assigned to one of three groups, A, B, or C. Each child individually watched a 30-minute television program that was interrupted for 5 minutes of advertising. The advertising was the same for each group with the following exceptions. The advertising for Group A included the Choco Zooties but not Apple Zooties. Advertising for Group B included Apple Zooties but not Choco Zooties. The advertising for Group C included neither Choco Zooties nor Apple Zooties. After the program, the children were offered a choice between the two snacks. The table below summarizes their choices. Do the data provide convincing statistical evidence that there is an association between type of ad and children's choice of snack among all children similar to those who participated in the experiment? Oh man, do the data provide convincing evidence? You know what that means. Full text. So, did I give myself space on multiple slides? I did. Man. Okay, that's great. So I'm going to put the null and at least most of the plan step on this slide, and I'll put do and conclude on the next. So I'm going to do the null up here. I need to figure out, is this a test for homogeneity, independence, or goodness of fit? Well, it's not goodness of fit because it's a two-way table, right? I have things going this way, and I have things going this way. It's not going to be goodness of fit. It's either independence or homogeneity. Homogeneity is, or experiments are always homogeneity. So we did an experiment, right? I've got random assignment. That's an experiment. So this is going to be homogeneity. So we're going to say the distribution of serial preference is the same for each ad group. You could also word it as the distribution is not different, but I think it's just easier to say this. So the alternate is the exact same thing. The distribution, it's basically the exact same thing. The serial preference is different for each ad group. There, I have stated. So that's my first step. Now I've got to move on to plan, so I need to name the test. We will conduct a chi-square test for homogeneity. So randomness. We have randomness because they were randomly assigned. The assignment is random. I'm sure there are at least 750 children that eat cereal / watch TV. I guess we just sampled children, so we'll just say children. Now I'm going to pause, and I'm back with a table of expected values. So remember, you're going to go into the calculator to get those. You can get the expected counts by hand doing row total times column total over table total, but I just went in and I entered the data, ran the test, and it spits out the expected counts for me. And so I made my table, I've shown the expected counts, and they're all at least 5. So that's my state and my plan. So the do step. The do step is also done in the calculator, right? The chi-square value that I got was 10.29. The p-value that I got was 0.005, and the degrees of freedom that I have are 2. Remember, that's rows minus 1, so r minus 1 times columns minus 1. For me, that's 3 minus 1 times 2 minus 1, which is 2. The calculator does spit it out, but I think you should know that. So all that's left is the conclude, and I'm going to do that down at the bottom where I can write more like a sentence. So at alpha equals 0.05, our standard alpha when it's not given, we reject the null. There's enough evidence to conclude, enough to conclude. There's enough evidence to conclude that there's a difference in distribution of serial preference among the ad groups. Ta-da!